All right, as I said in class, ladies and gentlemen, this is the video where I'm going to talk about how to do weak acid, strong base titration calculations. I want to emphasize that this question is worked through in the textbook. It's the sample problem 17.7 and 17.8. It's in the middle of chapter 17. So you can have a look at that problem in the book if you'd prefer to watch the video, because I go through the same stuff. And this is in our notes. I'm going through the problem that's in our notes. I've simply rewritten it so it's on the smartboard. And I'm just going to work through it. This is probably going to be divided up. I'll probably do part A and part B in one video and then part C in a second video, because these types of questions, they're a lot of work. You notice in class there are two parts, and the first part was the BCA chart, second part was the equilibrium problem, and that can take a little while. So first up, calculate the pH in the solutions formed by titrating the following amount of 0.1 molar sodium hydroxide into 50 milliliters of 0.1 molar acetic acid, and the Ka value for acetic acid has been supplied, 1.8 times 10 to the minus 5th. So this point here, part A, first up, 0 milliliters of NaOH, so no base has been added. So this type of question is really simply saying, what is the pH? If I rephrase this, what it's really asking is, what is the pH of 0.1 molar acetic acid? Because if you think about that, you haven't added any sodium hydroxide. So all you have in your flask is 50 milliliters of 0.1 molar acetic acid. There is no need for a BCA chart. So we are skipping part one. We're skipping that part of the question. And it has really turned into this statement: what is the pH of a 0.1 molar acetic acid solution? Now this is an equilibrium problem. You cannot do Henderson Hasselbalch because you don't have a buffer. This is not a buffer. This is just a weak acid. So we're going to do our 3 steps to solving an equilibrium problem. We're going to write a reaction, we're going to fill out a nice chart, and we're going to go to the equilibrium expression. So the reaction, we're dealing with acetic acid, so we're going to write a reaction for acetic acid. And remember, Mrs. Julian is using the abbreviation for acetic acid here instead of HC2H3O2. So acetic acid goes to H plus the acetate ion. That's step 1. We've written our reaction. Now we're going to fill out a nice chart for that. It says information from the problem that we have 0.1 molar acetic acid. We are looking for information about the H plus and the acetate ion. Get that negative in there, but we're not starting with anything there. It's just 0.1 molar acetic acid, and that's it. So minus X plus X plus X, and then 0.1 minus X, which we're going to say is approximately 0.1. This is X and this is X. Realistically, this problem from this point on is a very, very simple problem. It's just, what's the pH of a 0.1 molar weak acid solution. This is a primary topics question. This is absolutely a primary topics question. You haven't added any base. You don't need to recalculate anything. So all of this should look very, very familiar to you. You should feel very comfortable with this. So we filled out our ice chart. I made that assumption because the Ka value is very small. And now we're going to go to the expression. Ka expression, it's going to be H plus times OAC minus over HOAC, and we are simply going to plug in the values from our ice chart, going right from that ice chart. So now I'm going to do 1.8 times 10 to the minus 5th is equal to X squared over 0.1. And you're just solving at this point. You've done this type of problem before. The book actually doesn't walk through this type of question. They actually refer you back, and they say you already know how to do this. You did it in chapter 16 somewhere. So I'm not. That's why if you're unsure about that, that's the one thing that you won't get from actually going through the book. Solving. I get an X value of 1.3 times 10 to the minus 3rd molar, 1.34, excuse me. And if you look at what that represents, that's the hydrogen ion concentration. So we're going to take the negative log of that to get pH. Scrolling down a little bit. right? And this is, again, this is very, very standard stuff. I get a pH value of 2.87, and that is the answer to part A. We do want to do the check. We got an x value of 1.34 times 10 to the minus third divided by 0.1, multiplying by this by 100. This turns into 1.34% dissociation, which is okay because it's less than 5%, which was what we're looking for. So that's part A. That's part A of a weak acid titration problem. It's no different, absolutely no different from any sort of equilibrium problem you've done thus far. It is a primary topic. It's saying, okay, if you've added no base, what's the pH? It's basically just saying, what is the pH of a 0.1 molar acetic acid solution? And you can do that. You can absolutely do that. Things get much more interesting. So we took care of part A. Things get much more interesting when we move on to part B. What is the pH when we have added 45 milliliters of the sodium hydroxide into the 0.1 molar acetic acid solution? Ha 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 ha. Now this is going to be a two-step problem. Now this is what I was talking about in class. The first thing that we're going to need to do is a BCA chart. And then after the BCA chart, we need to do an equilibrium problem of some sort, and we'll figure out what specifically we need to do when we get there, when we look at what's going on after the BCA chart. What we need to do at this point, and the reason that it becomes a two-step problem, is we must recalculate how much, after adding in that 45 milliliters of sodium hydroxide, we sort of need to rethink about it again. And we need to say, all right, well, if I've added 45 milliliters of the NaOH, what is that going to mean for my amount of weak acid? How much of my weak acid have I neutralized by adding in that much of the base? That's the same BCA chart as you've done previously in titration when we did acids and bases earlier. So it's absolutely the same sort of thing. So that's the first part, and we'll do that first. Now, just like an equilibrium problem, it's very, very helpful to write a reaction. And the reaction that we're going to write for the BCA chart is neutralization. And you're always writing neutralization reactions. That's kind of what the BCA is standing for. How many moles do you have before neutralization? How many moles do you have after neutralization? And remember that BCA charts as well, this is about moles of stuff. So the reaction I'm going to write is going to be neutralization, and I'm going to put moles into it. So I've got sodium hydroxide and acetic acid. It's an acid and a base, so they neutralize one another. Ooh, notice, one way. This is a reaction that goes until one of the things is gone. This is not an equilibrium reaction. And we're going to create from this, we've got sodium acetate, and we have water. We need the complete reaction for this BCA chart. You can't get away with some of that slapdash stuff I saw a lot of you doing on the previous test, which was fine because it worked on the previous test, but you need the entire reaction for this. Now, moles. You start off by figuring out how many moles of the NaOH we have. So that's just using the fact that we have 45 milliliters of, so let's see, moles NaOH. We've got 45 mils, and it is 0.1 molar. So this is simply saying, all right, molarity equals moles over liters. So I've got 0.1 equals X moles over 0.045 liters, and we get 0.0045 moles of NaOH. You do the same process with the acetic acid. The acetic acid, we have 50 milliliters of the 0.1 molar solution, so we're starting with 0.005 moles of the acetic acid. I'm going to erase this because this is just showing how we get moles of everything we're doing in this problem. That's one of the easiest bits. But then we have to think about the products. And here's really what makes this type of titration problem significantly different from the titration problems that we've done in the past. The idea is the same, but there are big changes to the methodology. we have to plug in 0 moles for the acetic acid, because the whole point of the BCA chart is to figure out what is going to be in your titration flask after neutralization. And you need to figure it out for things that impact pH. So we're calculating the sodium hydroxide, we're calculating the acetic acid. We know we're doing that because we know they have an effect on pH. We're going to eliminate water. We're going to cross that off. Now the reason that we're crossing that off is not because water is a liquid. That's why we cross it out of ice charts. But we're crossing it off because it doesn't affect pH. Water, who cares if we generate some more moles of water? That won't impact the pH. There's already so much water there to begin with that the few moles we're going to generate will not have any kind of substantial effect. But sodium acetate, that's the salt that we're generating. This is a salt that comes from a weak acid, right? It's got that acetate ion in it. Conjugates. It is the conjugate base of a weak acid, right? That OAC, that acetate ion. This absolutely has an effect on pH. So we must figure out how many moles we are going to generate of the acetate ion in solution. The rest of the BCA chart will proceed as we've done before, but the big distinction is knowing that we need to fill in a column for that sodium acetate. So remember, with the BCA chart, the neutralization reaction proceeds until one of your reactants is gone. And because these are all 1-to-1, it's going to be the smaller one. So all, right, this is smaller. You want to make it go to 0. The way that you make it go to 0 is by subtracting 0.0045. This dictates your change for everything else. In order to neutralize all of the sodium hydroxide that's been added, you're going to use up 0.0045 moles of the acetic acid, and that's going to leave you with 5 times 10 to the minus 4th moles of acetic acid. So you're using up most of your acetic acid, all but 5 times 10 to the minus 4th moles. But you are also going to generate some sodium acetate. And this change, again, everything is 1-to-1-to-1. So this is going to be plus 0.0045. And you're going to create 0.0045 moles of sodium acetate through this neutralization reaction. That's absolutely critical to realize, that when you're titrating a weak acid with a strong base, you are generating the conjugate base of the weak acid, and that conjugate base has an effect on pH. So that this A row, this is describing your solution at after you've added that 45 milliliters of your sodium hydroxide solution. It's saying how many moles of the weak acid did we use up to neutralize it? How many moles of the sodium acetate have we generated through that neutralization process? But look at what we have. We have, HOAC. We have 5 times 10 to the minus 4th moles of HOAC. And we have 0.0045 moles of sodium acetate. Ladies and gentlemen, we have a buffer. That's what we have generated by neutralizing some but not all of the weak acid, and by generating some of the weak base, of the conjugate base, we have created a buffer in this problem. That's absolutely what's happened. So right now in our flask, we added that 45 milliliters of the NaOH, you made a buffer. You used up some of your weak acid, but not all of it. This ends part 1. All of this there, that was part 1. Part 2 becomes an equilibrium problem. And because we have a buffer, we can solve this using the Henderson-Hasselbalch equation, which is nice because the Henderson-Hasselbalch equation is kind of a shortcut to the equilibrium work, and it's a lot faster. But before we use, so the Henderson-Hasselbalch equation, I'll write that up right here. pH is equal to pKa plus the log of A minus, over HA. And it should be very apparent that A minus, that is our HOAC, that's our weak acid. I'm sorry, I'm pointing to the wrong thing. The A minus is the HA, and the sodium, and it's the acetate ion, I will be specific here, the acetate ion is the A minus. But BCA chart gives us moles. We don't need moles, we need molarity. So we need to recalculate molarity first before we start plugging anything into the Henderson-Hasselbalch equation. Now, Henderson-Hasselbalch, we're looking for pH. We can know the pKa. I say that we can know it because it's not given to us. pKa isn't given to us, but Ka is. So that's straightforward enough. And we can get A minus, we can get HA. We don't currently have them. We currently have moles. We need molarity. So you're going to need to take that next step and recalculate molarity. So the molarity of the acetic acid. Molarity is moles per liter. Well, how many moles do we have? 5 times 10 to the minus 4th moles. We figured that out through our BCA chart. So that's coming from previously. What volume do we have? Here's where previous titration problems are training you well for this type of titration problem. It's an additive volume. It's no longer the 50 milliliters of the sodium of the acetic acid. Now it's 50 milliliters of acetic acid plus the 45 milliliters that we added in with the sodium hydroxide. Added volume. Key. Must remember that. So doing this math out, we get a concentration of acetic acid of 0.00526 molar. What you've done is you've recalculated the concentration of your weak acid after some of it was neutralized by adding the base. Now we're going to calculate the concentration of the acetate. The acetate is 1-to-1 with the sodium acetate. So I know that whatever I calculate for the acetate is going to be the same, for the sodium acetate, it's going to be the same for the acetate ion. The moles, we used our BCA chart to figure out that we've got 0.0045 moles of the acetate ion. And again, added volume, the same volume of solution as before, 0.095 liters. Doing this math out, I get a concentration of 0.0474 molar. We can now take these concentrations to our Henderson-Hasselbalch equation, because now we have everything we need. We can get pKa, we have the concentrations, we have the molarity, so that's exactly what we're going to do. pH is equal to pKa, so the negative log of the Ka value, which is 1.8 times 10 to the minus 5th, plus the log, it's A minus over HA. So our A minus concentration, 0.0474 molar, and our HA concentration, 0.00526 molar. Right, those are our values that we calculated just from above, so we're plugging those right in. And I always think using Henderson-Hasselbalch, it's good to kind of write down some intermediate steps just in case we're not punching things into our calculator correctly. So the pKa value is 4.74. When I take the log of those particular numbers, sorry, not log, 0.955. So calculate it out, a pH value of 5.69. Now, depending on how you round, that 5 might boost it up to 5.70. I'm not going to quibble about something like that, but that's the pH, and that's the process. So step 1, BCA chart, recalculate molarity. For step 2, a buffer problem. Henderson-Hasselbalch, you have both weak acid and its conjugate base in the solution together, so you can use Henderson-Hasselbalch to calculate pH there. I'm going to stop this video now because it's about 20 minutes. For part A and part B. Part C is longer, and so I'm going to separate this out so that you can easily separate it out on your own. Again, this part B is sample problem 17.6 in the textbook. Part C is the next one.